Okay, this will be the lecture for Chapter 13. We're moving on into liquids. What we're going to cover is we're going to introduce a new concept called pressure and how that's related to liquids, actually all fluids, both liquids and gases. We'll talk about how we can have buoyancy, which is kind of why things float. And we'll put some numbers to that using Archimedes' principle and talk about this principle of flotation just a little bit more. And we'll kind of finish off with something called Pascal's principle. So if we had a floor right here and we said, well, what if you stood on the floor with one leg versus standing on the floor with two legs? What can you say about the force that you exert on the floor? Now, keep in mind that force is going to be your weight, which is your mass times gravity. And I don't know about you all, but mass times gravity here looks about the same as the mass times gravity there. So the pressure, the force should be the same. Now that we're dealing with fluids, we need to talk about pressure, and no, maybe not pure pressure. Now we're going to be talking about the pressure of objects. And if you think about it, up until this point, we've been dealing with boxes where I could kind of take my finger and I could apply a force to this box and it would move. But now we're talking about liquids, and we know that if I had some liquid in a tube and it was didn't just randomly leak out of there, if I tried to stick my finger into this, then it would just go right into it. So kind of what I have to do is I have to cover this end of the pipe with a piston or something like that, and now my finger can apply some force, but it's not applying it to a point, it's actually applying it to that whole area. So when we do that, we need to define a pressure, which is essentially going to be defined as a force per unit area. Or we can kind of shorthand this and say pressure is going to be equal to force divided by area. Now the unit of force is going to be a Newton, the unit for area is going to be a square meter, and this is a special unit that we've seen time and time again, so it's called a Pascal, so a P-S-C-A-L, and if you see a number of 50,000 Pascal or 50,000 pascals, that's simply a pressure. In the English system, we might talk about inflating your car to 50 psi. That's a pound per square inch, or could even kind of write this guy out, a pound per inch squared, so a unit of weight per unit of area. So now let's come back to my question. If we stand on 1 foot rather than 2 feet, then we know that the force we apply is going to be the same. How about the pressure that we exert? Well, I don't know about you guys, but taking a look at this guy's foot versus this guy's 2 feet, I would say that the area is less for this guy, since pressure is equal to force divided by area. As I divide by a smaller number, I would expect the pressure to go up, so there's going to be more pressure exerted by this guy than by that guy. Now, kind of as an aside, if you've ever taken someone out on some wet grass that was wearing high heels, maybe an example like this, just don't do it. Guys, girls, you know what I mean. Guys, just don't do it. This thing right here has a really small cross-sectional area, so it puts a lot of force downwards, and if you go onto some wet grass, it'll sink into that like a hot knife through butter. Trust you me, I found that out on my wedding day. Now, pressure can kind of play games with us, and if you take something that's relatively large, and you take something that's kind of small, maybe you can hold each one of these guys in your hand, and you may feel like this guy weighs more, but in reality this guy right here is actually the one that weighs more. Kind of the difference is this guy spreads that weight out over a fairly large surface area, so it feels like this one weighs more, but in reality this guy does. Now, pressure is also how snowshoes work. If you were to think about, I'm just going to call this your boot print, and your boot print as you step down onto some snow, well, much like the high heels, it could possibly punch through some snow, but if you were to take that same footprint, I'm just going to erase this guy right here, and you're going to put that foot onto some snowshoe, or onto a snowshoe, what you're doing is that you're spreading out your foot over a very large area, kind of reducing the force that you put into the snow, which is why you tend not to sink in. pressure also answers the age-old question, you know, why doesn't that hurt? I mean, we all know that if she was trying to lay on just one nail, well, that wouldn't be too pretty. But if you take the force that is, you know, her body weight, and you put that on one nail, then yeah, that's going to be a lot of pressure. But if you spread that out over a very large area, remember pressure is equal to force divided by area, we're not really messing around with the force, that's just her weight, but we are increasing the area, decreasing the pressure, and she's able to read this physics textbook and be quite happy. Now, one type of pressure you may have heard of is called atmospheric pressure. You can flip open the app on your cell phone or your phone and check what the pressure is. And two things I want to say with this is we're going to talk about this a lot more in the next chapter, but pressure is going to apply to both liquids and to gases. Both of these guys are technically fluids, and so pressure is going to apply for both of them. And kind of what atmospheric pressure is if you just kind of take, you know, some chunk of area right here and you say, wow, check this out, I've got all this air above me, right? We calculated the other day that you know, the weight of the air in the room was like 125 pounds. Think about the weight of the atmosphere above you, and the atmosphere extends for, you know, thousands and thousands and thousands of feet. So we have all this weight above us kind of pressing us down. So here we are at the surface of the Earth, and we're going to feel some pressure due to that, and it's going to be the pressure due to the atmosphere, and actually it's going to be 101,325 pascals. So it's going to be about 10 to the 5th pascals. The pressure due to the atmosphere is actually quite a large number, and I'll talk a little bit more about this in the next chapter. So now that we've kind of dilly-dallied a little bit talking about this new concept called pressure, let's, you know, talk about how it relates to a liquid. So if I've got some liquid, and I'll just use water for, you know, the sake of just for the sake of simplicity. So there's kind of my chunk of water, and I'm going to go ahead and I'm just going to put a piston right here and a piston right here. How do we make water flow? Well, we have to apply pressure to it. And what we can kind of do is we can say, okay, well, I can apply some pressure right here. And a liquid is very different than a solid, in that a solid can't really flow. A solid's locked into this nice crystalline structure. A liquid is not, so these molecules, yeah, they're kind of loosely connected to one another, but they can definitely flow. And one thing to keep in mind is that it's not going to compress. Liquids are not compressible, so they're not going to change volume, kind of like a gas will. And they're going to flow from regions of high pressure to low pressure. So right over here, this is my region of high pressure. There's low pressure, I have none. I could put, you know, a little bit of pressure right here, and you would still kind of say, well, this is high pressure, this is low pressure, so this liquid is going to go in that direction. So, you know, pressures really are just kind of like forces for liquids or fluids. Now, one thing you may hear is that water seeks its own level, and if I were to take this guy and kind of fill it up with water, that's going to be my horrible blue squiggle right here. And what water is going to do is it's going to seek the same level in all of these containers. So it's going to fill up to there, 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 it's going to fill up to there. Really what it's doing is it's seeking the same pressure. So it's seeking the same atmospheric pressure on all of these guys, and size and shape doesn't matter. So we have the atmosphere pressing down here, pressing down here, pressing down here, pressing down here, and pressing down here, and so water doesn't care about the shape of the object that it's in, it only cares that the pressure on it is the same. But what about the pressure inside of liquids? And to kind of work our way there, I want you to kind of think about just blocks of wood right here. Here we've got one block of wood, here we've got two blocks of wood, and they all kind of have the same mass. I think we would all agree that this one puts more force on the table, so this one's going to put more pressure on the table. Now if we went ahead and replaced those blocks of wood by liquid, then you would probably be able to argue that this one puts more pressure on the table. And if we were to cut this guy in half, then you would argue that, you know, this one's going to put the most, this would be in the middle, and then some smaller one would put even less. So what we can kind of do is we can kind of relate the height or the depth of this container of water to the pressure. And what we're going to do is we're going to say that the pressure is going to be equal to the density times gravity times the depth. And the deeper we go in the water, then the more pressure we feel. And that's going to essentially be able to explain to you why you feel all that pressure in your ears when you dive down to the deep end of the pool. So, kind of a nice little equation to have. Now, we can also say that the pressure is going to be equal to the weight density multiplied by the depth, where these two guys just kind of make up the weight density, and that's the depth as well. But again, I'm not a big fan of the weight density. What this kind of tells you is that the pressure is going to be going to be depth dependent. Again, density times gravity times depth. You don't see the word volume anywhere. So it doesn't matter whether you're in a swimming pool or the Atlantic Ocean. What the pressure that you feel is not due to the volume, it's only how deep you go. So if you were to think about a fish being here, or here, or here, or here, then that fish is going to feel the same pressure. It doesn't depend on volume, it only depends on depth. And this fish right here, doesn't matter whether he's here, or there, or here, or here, he feels the same pressure anywhere along the same depth. So let's just do some quick little calculations. How much pressure would you feel in a large but shallow lake at the very bottom, or a small but deep lake? Keep in mind that large and small don't make a difference in the world. So the pressure is going to be equal to the density times the gravity times the depth. So in this case, it's going to be 1,000 times 10 times 5. So it's going to be 50,000 pascals, and yes, I know that is a big number, and yes, it should be that large. So right over here, we're going to say the same thing. It's going to be 1,000 times 10 times 10, and so the pressure here is going to be 10,000 pascals. When we're dealing with pressures, very typically we are talking in the 10 to 100,000 pascal range. Now, anyone that has a fish tank kind of knows that a siphon works. Maybe you don't know how a siphon works, but if you've got two jugs of water, jug number 1 and jug number 2, and you were to stick a pipe in there and you sucked just enough water such that it was just about right there, what's going to happen is, well, take a look at this guy right here. This water is at a height or a depth, really they're kind of the same thing, and so right up here we're going to have high pressure, right over here we're going to have low pressure, and what's going to happen is that the water is going to flow from a region of high pressure to low pressure. And the Romans could have saved themselves a lot of aqueduct work if they would have essentially realized this. They had all their reservoirs pretty high up here on the mountains, and what they did is they kind of built some pipelines, and when they got to about this level of the mountain right here, is they built this nice pretty aqueduct system, and so that way the water would flow down here to where Rome is. But if you think about it, it doesn't matter what happens in the middle. That water could perfectly well flow down, flow back up, and come back down to Rome. The only thing that matters is this is going to be high pressure, this is going to be low pressure, and the middle doesn't matter. It's only the endpoints that matter. And again, kind of depth and height are kind of the same thing. You could even, if you really wanted to, write pressure is equal to density times gravity times height. And here we have the giraffe's heart, and if a giraffe were to lift its head up really high, then what's going to happen is the heart needs to supply enough pressure in order to get the blood up that high, and that's why giraffes have this like monstrous heart. It's like the size of a big dog. This is also kind of the reason why when the doctor takes your blood pressure, he or she takes it in your arm. Why is that? Well, it's because of this guy right here. They want the pressure in your heart. They don't want the pressure in your leg. Your leg is deeper than what your heart is. So we care about heart pressure. So just take a second here and think about where water pressure is going to be the largest, or if we wanted to increase the water pressure for a town, then is it going to be taller? Well, pressure is equal to density times gravity times height or depth. So definitely this one, whether it holds more volume, so increasing the volume, and we all know that that has no effect, so it's not going to be A or B, and it's not going to be C. You could also perhaps argue that if you used something that was a different density, then you could also increase the pressure. One way you could do that is to use salt water, but I think we could all agree that we don't want to be drinking salt water, so maybe that's not the most viable option.